So in this video, we are going to talk about quadratic functions. These are second degree functions. Okay, so these are of the form f of x equals ax squared plus the letter b times x plus c, where a, b, and c are real numbers, with a not equal to 0. If a was equal to 0 here, it'd be either a linear or a constant here. Okay. The vertex is either the max or min of a quadratic function. So like the vertex, that would be the maximum right there. Like if you had another quadratic function and it was like this, that would be the minimum. Okay. So the vertex is found by negative b divided by 2a, and then evaluated at negative b comma 2a. Because if you think about it, this is an xy coordinate, and y is equal to f of x. So that's why we use this format here to find the vertex, okay, for a quadratic with coefficients a, b, and c. Okay, so let's start out with the most basic quadratic, and this is f of x equals x squared. Doesn't get any more simple than that. So let's make a table. So negative 3, negative 2, negative 1, 0, 1, 2, 3. And in our table, I'm going to plug in those values, see what I get. Okay, so if I plug in x squared, so I'd square negative 3, I get 9. If I square negative 2, I get 4. If I square negative 1, I get 1. If I square 0, guess what? I get 0. 1 squared is 1. 2 squared is 4. And 3 squared is 9. Looks like we see a pattern start to develop. Let's make a little sticky and see if we can't graph this thing. Well, here we go. Okay. So at x equal to negative 3, we have an output of 9. So I go over 1, 2, 3, and I go up 1, 2, 3, 4, 5, 6, 7, 8, 9. So my first dot is here. Then I have negative 2 and 4. So I go over negative 2 and up 1, 2, 3, 4. And then negative 1 and 1. And then 0, 0. That's the origin. And then guess what, guys? This kind of connects just like this. Okay? The mirror image is on the other side. So 1, comma 1, 2, comma 4, and 3, comma 9. So it's the mirror image. This is the positive branch. This is the negative branch of the square root. Okay? Now, we have an axis of symmetry. If I split this up right down the middle, we see that it's symmetric. It's the axis of symmetry here. This is the equation x equal to 0. The axis of symmetry runs straight through the vertex. The vertex for this one, the vertex is 0, comma 0. So that x coordinate or component of the coordinate actually tells us the number x equal to that number is the axis of symmetry. Okay, so the vertex helps locate the maximum or the minimum of the quadratic, but it also tells you the axis of symmetry where it splits it basically in half. Okay, so what we're going to do is we're going to take this quadratic and we're going to do some transformations on this quadratic, see what all transformations we can make. So the first one is g of x equals x minus 3 quantity squared. Okay, we'll want to find the vertex, x-intercept, 2 points on the graph. Okay, so if you have no idea what this looks like, then just start plotting points. You can always use this idea of making a table. Okay, so we can make a table, x and g of x, which is x squared, or x minus 3 quantity squared. And so if I plug in 0, 1, 2, 3, 4, see what happens. If I plug in 0, I get 0 minus 3 squared, which is 9. 1 minus 3 is 2. 2 squared is 4. I'm sorry, negative 2 squared gets you 4. 2 minus 3 is negative 1 squared. I get 1. 3 minus 3. Guess what, guys? 3 minus 3 is 0. And squared gets me 0. 4 minus 3 squared is 1. 1 squared is 1. And I think you can see the pattern. If we went from 9, 4, 1, 0, then 1, the next one might be 4, and then 9, and going like that. Okay? So let's see if we can't graph this. So if I graph this at 0, at x equal to 0, go up 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, if I go over 1, I go up 4, 1, 2, 3, 4. Go over another, I go up 1, go over 3. All right, and then so this point here is 3, 0. And then it looks like it goes back up again at 4. I go over to 1. At 5, if I plug that in, I'm going to get 4. At 6, I plug that in, I'm going to get 9. And so you can see here, it looks like we're going up and we got that same image going on here. Now the vertex here is 3, 0. So the vertex is 3, 0. The x-intercept, where do we cross the x-axis? Do we? Yeah, we do at one spot, and that one spot is the vertex. So the x-intercept is found when y is set equal to 0. Well, we don't have a y here, so we have a g of x equal to 0. If I have 0 equals x minus 3 squared, if I do the square root method, I have the plus or minus square root of 0, which is still 0. And then I have x minus 3, and so I add 3 to both sides, and this is where x equals 3 comes in for our x-intercept. Okay? Now graph 2 other points. Well, if you make a table, then you've got plenty of points, right? You just pick 2. Pick your favorite 2. I'm just going to pick 2, 1 and 4, 1. Okay, so that's right there, and that's right there. All right, so you just got to pick 2. I don't care which 2 that you pick. One way you can do this is in your calculator. If you go into your graph, so I'm going to delete these. So go into your graph and do parentheses, x minus 3, close parentheses, square it, enter. And so graph, you can see the graph there. The vertex is at 3, 0. But to pick a point, if you do second table, then you can see all these points to choose from that you want to. And so 0, 9 is a point, 1, 4 is a point, 2, 1 is a point, 3, 0 is a point, but you already used that one. 4, 1 is a point. So you just pick one or two, however many they tell you. And so that's where you can get a list of points from. Okay? All right. One thing that could have saved you a whole lot of time is understanding transformations. If I look at this graph right here, okay, if I look at that graph, what's happening with this graph here? Well, we're getting shifted, the quadratic, the f of x, the parent function. This is the parent. Okay, the parent function looked like this. It was x squared, right? Kind of like this. And what happened to the x squared thing? Well, it got transferred. It transferred. It was horizontally shifted to the right. How many units? 3. So what happened was we went to the right 3 units. So if I have a number on the inside of the parentheses here, that tells me it's either going left or right. It's a horizontal shift, okay? So since I have this minus 3 here, that's telling me I go to the right 3, okay? Let's do another one. Let's do h of x equals x plus 7 all squared. Ooh, anyone want to take a guess what's happening to this? So if I subtracted 3, I went to the right 3. If I add 7, what is that going to do? Yeah, that's going to make us go to the left 7. Okay, I go to the left 7. What goes to the left 7? My parent function, x squared, goes to the left 7. So this really does help us out in being able to do these problems a whole lot quicker. So now I know the parent looks like this, and its vertex is at 0, 0. But if I shift it to the left 7, now all of a sudden I know, okay, my vertex is negative 7, 0, right? If I go over 1, that means I'll be at negative 6 and 1. If I go over 1 this way, I'll be at negative 8 and 1. So that helps me get 2 other points really quickly. Looks like my X-intercept is the same as the vertex. So it really does help if you understand transformations, then you can avoid all of this table business, okay? So that shows me what I do going left or right, okay? What about if I have like j of x equals x squared minus 2. What's different about this one? Well, instead of having a plus or a minus on the inside of my parentheses like I did there, now I've got the negative on the outside. Okay, so it's just x squared and then minus my 2 on the outside. So what does this tell me to do? Okay, well, if you're having trouble, you can plot some points. So x, and let's just do negative 2, negative 1, 0, 1, 2. And then I have x squared minus 2. So if I square it, negative 2 squared minus 2, so that's 4 minus 2 is 2. And then negative 1 squared minus 2, that's 1 minus negative, so minus 2 gets me negative 1. And then 0 squared minus 2 is negative 2. 1 squared minus 2 is negative 1. And then 2 squared minus 2 is 2 again. So my points to plot are here. So what's happening? So I've got my graph. Okay, in the original x squared, looks like this. Okay, that's x squared, right? Now, what's happening? I'm literally taking this and I'm shifting it down 1, 2. Okay? It's shifting down 2. Right? So how do I know? Negative 2, comma 2. So negative 2 and then up to 2. Ooh, what have I done? Okay, that was not, I didn't get my dots exactly right. You know what, let me just back up here. I'll get these dots better. Let's change this. All right. So, oh man, I did my dots wrong again. All right. So let's see. Up to this. All right, so this is x squared, okay? Now what's happening? To plot these dots, that's negative 2, 2. So negative 2, 2. So if I go over negative 2 and up 2, there you go. This is negative 1, negative 1. So I go over 1, down 1. 0, negative 2. And then 1, negative 1. And then 2, 2. Okay? So now my graph looks like this, and this is x squared minus 2. Now what is happening here? This x squared graph is getting shifted down 2 units, okay? Down 2 units. So once again, I goofed the vertex. The vertex should be right there. Okay, so let me delete that real quick. Okay, but you get the picture. All right, so this thing gets shifted down 2, okay? So if I see this negative on the outside, that tells me that I go down 2, okay? Now say I have L of x equals x squared plus 5. What is this going to tell me to do? That plus 5 is going to tell me to go up 5. Okay, up 5. So now all I have to do is take my parabola and shift it up 5 units. So now the new vertex is 0, 5. Okay, and there's no x-intercepts. Never crosses this x-axis here, right? And it makes sense because if we set this equal to 0, what would happen? I'd subtract 5 from both sides. I'd have negative 5 equals this x squared. When I take the square root, now all of a sudden I have x equals plus or minus I square root 5. Well, this is imaginary, so no real intercepts, okay? There's no real intercepts. There's only imaginary complex solutions, okay? There's one more thing that we're going to do to our parabolas. Instead of shifting up, down, left, and right, we can either take a parabola and we can stretch it, or we can make it wide, okay? So it's either going to be narrow or it's going to be wide, okay? And that all depends on the coefficient in front of the squared term, okay? So say I take k of x equals 6x squared. What does that do? 6x squared. Well, it takes my parabola that's like this. So that's x squared. And if you think about it, at 0, 0, right? And then this is at 1, 1. And then this here is at 2, 4. Well, if all of a sudden I change this to be this new equation here, what's going to happen? If I plug in k of 0, I get 6 times 0 squared, which is 0. But k of 1 is 6 times 1 squared, which is 6. So now at 1, I'm actually going up to 6. So this is getting very steep very fast. Okay. Same thing on this side. It's getting very steep, very fast. So that's 6 comma 1. K of 2 is 6 times 2 squared, which is 4. So that's 24. It's like way up here is 2 comma 24. So you see that that's actually growing way quicker. It's way more narrow. Okay. The other thing about it is that if the number is positive, okay, the coefficient in front is a positive number. Positive numbers have a minimum, okay? So you're smiling when you're positive. So we are concave up, okay? Now, negative numbers, all right? So let's take another example. So let's take like I of x equals negative 1/2 x squared. So negative numbers are the opposite of positive. Instead of being concave up, a negative number is concave down. So concave down, we got a frown. Concave up is like a cup. Okay, so a cup, you think about a cup, it holds water, right? Okay, so concave up, we're smiling, positive. Negative coefficient in front, concave down, we're doing a frown. Okay? So if I graph this, we know right off the bat that it's going to be concave down. That's a negative x squared. But then we've got this 1/2 factor. Now what does 1/2 do to it? Well, 1/2 literally cuts it in half. Okay? It cuts it in half. So instead of going all the way down to 2 comma negative 4, we're going to go halfway down to 2 comma negative 2. Okay? So my graph now instead goes half down, half as fast. Okay? So it's still going down, but it's just going down at half the speed as the other. Okay? So it's more wide. So there's a trick here. Okay? If the coefficient, so say we have, and this is going to kind of sum everything up, okay? So say I have like some f of x equals a x squared, okay? If that a in absolute value is greater than 1, then we're narrow. Okay? So that's like, would be like if I had like f of x equals 5x squared, or g of x equals negative 3x squared. In absolute value, negative 3 is greater than 1. Okay? Absolute value is how far we are from 0. Now the other scenario is if the absolute value of a is less than 1. If it's less than 1, then we're wide. And examples of that would be like f of x equals 1/2 x squared, okay? That would be wide. Or g of x equals 4/5 x squared, negative 4/5 x squared, okay? Now, these would be examples where the absolute value of a is less than 1, okay? Here's the deal, though. If this is a positive number, that means we are concave up. If it's a negative number, we are concave down. So here it's a positive number, so we're concave up, and here it's a negative number, so we're concave down. Okay? So if a is greater than 0, then we open upward. If a is less than 0, then we open downward. Okay, opening downward would be like this. Okay, opening upward would be like that. All right. So that kind of sums up your stretching and compressing vertically.